Hello, class. So this is the fourth video in section 4.6. It is just a theorem. Here it says theorem 10. I'm thinking that's the number theorem in the book, but for us, this is the third theorem. The first theorem was Roge's theorem. The second theorem was the mean value theorem. So this one is called theorem 3. It really doesn't have a name, and we're not going to prove it. We're not really going to do an example about it. I'm just going to tell you what it says, because this is going to be used more as a stepping stone for the next theorem, which is other than the mean value theorem, the second big theorem in this section. Okay. So what does this theorem say? If f is differentiable, so first assumption, and f prime of x, so its derivative, equals 0 at all points of an interval I. Right, so those are the two assumptions. F is differentiable, and the derivative equals 0 on the interval I, on the whole interval I. Then what can we say about f? Then it must be the case that f is a constant function. So the reason why I don't want to do an example about this or prove it is because I'm going to ask you to prove that this is the case, that if you have a function that's differentiable and derivative is 0 on the whole interval, that it actually has to be a constant function. I'm going to ask you to prove this in the next homework. And I'll give you hints on how to do it. It's not actually that bad. It's kind of like if you know how to approach it, it's kind of like just following a logical sequence of steps. So this I'm going to write. We're going to leave it as a extra credit for the next homework. So for now, just basically is just memorize it or understand what the statement is saying. Now, the reason why this is useful is the next theorem, which here again, it says theorem 11. For our purposes, this is theorem 4. Okay, so what is this theorem? And this is going to be very important when we start talking about integral calculus. Very important. One of the most important theorems of integral calculus is going to depend on this one here. So this actually has a name or a description. It says functions with equal derivatives differ by a constant. In this one, we will do an example and we will actually prove it because, like I said, it's very important for when we start talking about integration. So what's the theorem say? If you have two functions such that f prime of x equals g prime of x for all x on some interval I, then f of x minus g of x has to be equal to a constant on this interval. Okay, so said in other words, if the derivative of f equals the derivative of g on some interval I, then f minus g is a constant, right? That's the difference. Difference means subtraction. So let's say we want to prove this. We're going to prove this using theorem 3. So first we're going to define this function, h of x. We're going to call it f of x minus g of x. Now, since f prime and g prime exist on I, right, we're given that by assumption because we're saying that the derivatives are equal. Well, the derivatives must exist. So for sure, f prime and g prime exist on I. And we saw a theorem before that said that a sum or difference of differentiable functions is also differentiable. So let me write that here. Since the difference of differentiable functions is differentiable, then we know that h of x has also have to be differentiable on I, right? Because we're focusing on this interval I. We don't know any other information about f and g outside of I. All we know is that on the interval I, they're differentiable and the derivative is equal. Okay. Now, by definition of derivative, right, we know what h prime of x is. We can calculate it. You just take the derivative of each component, right, of each term. That's the sum or difference property of the derivative. Right? This is f prime of x minus g prime of x. Now, what do we know by assumption? We know that f prime equals g prime on I. right? So if we subtract them, we get 0. Right? So we get h prime of x equals f prime minus g prime, just by definition of h and how you take derivatives. And by assumption, since f prime equals g prime, this is equal to 0 on I. Okay. So the derivative of h equals 0 on I. What does the previous theorem tell us? Well, if you have a function whose derivative equals 0 on an interval, then it must be a constant function. Here we have a function, h of x, whose derivative equals 0 on the interval I. So by theorem 3, h has to be a constant function. Right? So what's a constant function? Well, that means h of x equals c, right, for some constant. But remember how h of x was defined? Right? H of x was f of x minus g of x. Okay, so substituting that in, we get our conclusion. We wanted to show that f of x minus g of x was c, meaning that f and g differ by a constant on I, and that's what we have. F of x minus g of x equals c. Now this is very important. And in fact, just the statement itself is very powerful. It's telling you whenever you have two functions whose derivatives are equal on some interval, then they're basically, then they differ by a constant. Right? Another way you can write this is f of x equals g of x plus c. So one function is the other function shifted up or down, whatever, depending on whatever c is. Again, this is going to be very useful for us in integral calculus. Okay? So keep this in the back of your head. Very important theorem. And now let's just go ahead and finish it off. Hopefully this works with one example. Okay. So example 4. Verify that the functions f of x equals sine squared x and g of x equals negative cosine squared x have the same derivative. What can we say about f minus g? Okay. So let's do the first part. Let's verify that they have the same derivative. So basically just find what the derivatives are. So what's the derivative of f? You just have to use the chain rule here. We've done this a couple of times. So derivative of the outside, leave the inside the same, multiply by the derivative of the inside, derivative of sine is cosine. What's the derivative of g? Same thing. You can leave the negative outside. Right? So forget about it. Just take the derivative of the rest. Take the derivative of the outside, leave the inside the same, multiply by the derivative of the inside. Derivative of cosine is negative sine. You have two negatives, just multiply together to get a positive. So we end up with 2 times cosine times sine. And we verify that in fact f prime equals g prime. Okay. Now, what can we conclude about f minus g, right? So by theorem 4, since f prime of x equals g prime of x, right? So we have to say on what interval. Here, this is for all x. So here we can just say the interval being negative infinity to infinity. Then we know what must be the case, that f and g must differ by a constant, right? So f of x minus g of x have to be equal to c, right, for some constant c. Okay. And that answers the question, right? We verified that the derivatives are equal, and by that we can conclude that f and g differ by a constant. Right? So that's what we can conclude about f minus g. We can actually verify that this is true. So this doesn't tell us what the constant is, right? It just tells us that f and g differ by a constant. We can actually find what that constant is. In this case, it's very easy. Because if we take f of x minus g of x, well, that's sine squared x minus negative cosine squared x. Right? Minus minus becomes plus. So this is sine squared x plus cosine squared x. And as we know, or we've seen before, whenever you have sine squared plus cosine squared of the same angle or same input, this is always equal to 1. So what do we end up with? We end up with f minus g equals 1. So we do here verify that f and g differ by a constant. What we found in the previous part is using the mean value theorem. Here we can actually find what the constant is. Now, it's not always easy to find this constant, but for integral calculus, it's going to be enough for us to know that they differ by a constant. Okay. So that's how you use this theorem. Theorem 3, again, is mostly a stepping block for theorem 4, but it's still useful to know that if you have and it's kind of like a special case of theorem 4, right? So they're both useful. Again, we're going to see them show up again in integral calculus. And this is the last thing in this section. So 4 theorems, theorem 2 being the mean value theorem and theorem 4 are the 2 most important, right? And you'll see them show up later.